Yeah, I'm going to present our tackle paper. As the title says, it's on speech translation, so we assume we have an acoustic utterance recording given and want to translate that into text in a foreign language. Speech translation is useful in a lot of different ways. To name just a couple, we could use it to realize a two-way dialogue situation between two people of different language backgrounds. We could also use speech translation to attend a talk or a lecture given by a person who's speaking in a foreign language, and the speech translation can help us to translate that into our own language. And there's a lot of other possible applications, and in practice these are typically realized using a cascaded approach, where we have the source speech, we feed that through a speech recognizer to obtain the source text, and then we feed that through a machine translation model to obtain the target text. And that's okay until we get to the point where the speech recognizer makes an error, and that often leads to propagating errors to the target side, and that's all caused by the fact that we are making this early decision halfway through the translation process. So recently researchers have started investigating end-to-end modeling as an alternative, where the idea is to have a single model that does a complete step from source speech to target text. And there's a lot of appealing points to that. One is that we can jointly train all of our involved parameters. Another interesting point is that the thing becomes more simple from an engineering point of view, because there's less dependencies between components. We can avoid the error propagation problem, and it also can become more computationally efficient if we have to carry around and run just a single model as opposed to two models for doing the same thing. So that all sounds very nice, but in practice there's a big drawback also, which prior work has not looked very much into, and that's related to the data situation. So if you think of the cascaded approach, we generally train that on a speech recognition corpus for training the ASR, and we train the machine translation model on MT corpus, and both of these corpora can be completely unrelated, and we have a lot of choices available, so in lots of different languages and language pairs. So the data situation for that is quite nice, but once we move to end-to-end modeling, it looks a bit different. So there we need a corpus that pairs source speech with a target text, and unfortunately there's only very few corpora available right now. And so that means if we want to make end-to-end speech translation practical and able to compete with cascaded approaches, we really need ways to effectively make use of this kind of auxiliary speech recognition and machine translation data. So let's talk a bit about prior work. The first kind of prior work simply applies the sequence-to-sequence model to the problem, where the inputs are the source speech and the outputs are the target text. So looking in the data chart, that is going to be trained on the end-to-end data, which can be limited in practice. Some follow-up work extended that into a multi-task training strategy, where we add auxiliary encoders and decoders, and that can help us to include different kinds of data into the training. For example, if we wanted to add speech recognition data into the model, we would take the encoder from our actual speech translation model, pair it with a auxiliary decoder that decodes the source text instead of the target text, and train that with the ASR data. And because parameters are shared with the final speech translation models, we can hope that the model is going to improve. So that is a way to make use of potentially large auxiliary data, but it's unfortunately not a very good way. To see that, let's take a look at some experiments. So here we have the blue score for a cascaded model trained on the MT and ASR parts of a speech translation corpus we can compare that against a direct model trained in a multitask fashion on the same data, including the end-to-end portion of that data. So on the left side we have the 100% data case, and there the direct model is doing a bit better. And to keep the comparison fair, we made the architectures for both the cascade and the direct model as similar as possible. And unsurprisingly, when we take away parts of the data, the accuracy drops. But now the interesting thing is what happens when we keep all of the auxiliary data in the training. So all of the machine translation and speech recognition data we keep, but we take away parts of the end-to-end data. And we can see that in the case where we only use 25% of the end-to-end data, we have this large gap to the cascade, despite the fact that we're actually using more data than the cascade. So that shows us that we have a quite serious problem with data efficiency for this direct type of model. So that brings me to the second type of prior work that I want to consider, which is called the two-stage model. It looks very similar to the cascaded model because we first create a source text and based on that create a target text. It is end-to-end trainable, however, because instead of passing on the discrete output tokens, we pass on the hidden decoder states from the source text decoder to the translation stage. So it is end-to-end trainable, but it also, like the cascade, suffers from the error propagation problem. So that now leads me to the proposed model, which we call the attention passing model, and it aims to address both of these problems, namely the data efficiency problem and the error propagation problem. Like the previous models, it can also be trained in a multitask fashion, which is a requirement in order to get the auxiliary data into the model. So we can train this part of the model on ASR data, this part of the model on NT data, and then we need some end-to-end data to also train it fully. And in addition to that, we try to work around the error propagation problem, and to see that, let's take a look at what exactly is happening in the model. So the basic idea is, instead of passing on hidden decoder states to the translation stage, we pass on attention context vectors. So here we apply the first, we decode the source text, and for generating the first output of the source text, the attention models that this first red part of the audio is relevant. So this first red part is the part of the audio that's represented by this first source text output, and the context vector summarizes exactly that part of the audio. So we copy over that this context vector over here. We continue to the next token. Here again the attention tells us that the green part of the audio is representing this second output on the source side, and we will use that context vector as a second input for the translation, and we continue on. And in the end, those context vectors are going to be translated into the target text. So the whole thing is again end-to-end trainable. Importantly, we no longer make an early decision on the source text, at least not from the translation point of view. Instead, we only make an early decision on the attention, and we observe in practice that the attention is quite robust against decoding errors. So even if the source text decoder makes a lot of errors, the source side attention is quite robust in practice. To get good results, we add a few refinements to the model. Firstly, we share these RNN parameters in these two places. That's in order to make the multitask training more effective. Secondly, we add the drop block out on the source text decoder between the decoder hidden states and the output layer, and that's supposed to make the context vectors more informative, because half of the time the source text output layer will make its decision only based on the context vectors, because the RNN states are dropped out. Thirdly, we add this additional loss. So if you observe, we have these shared RNNs, but they have two different inputs in both places. Once it's a character embedding and once it's a context vector, and this loss tries to make those two inputs more similar. And finally, this is optional. We add cross connections between the dropped out source text decoded states and the inputs to the translation stage, and that's in order to find a kind of compromise between revealing more information to the model while keeping the impact of error propagation to a not so high level. Okay, so for the experiments, we conduct experiments on the Fisher portion of the Fisher-Colholm Spanish to English speech translation corpus. So it's a telephone translation corpus with audios, transcripts, and translations, about 160 hours of data. So looking at the full data condition, this is again what we saw before. The direct model is doing quite a bit better than the cascade. The two-stage model from prior work is falling in between, which probably makes sense because compared to the cascade, it's adding end-to-end trainability. Compared to the direct model, though, it suffers from error propagation. So these are the baselines, and we can see that the attention passing model, especially after adding the refinements, does quite a bit better. And now we're also interested in the data efficiency, and this is showing a similar experiment to what I showed before, where we keep all of the auxiliary machine translation and speech recognition data in the training, but take out or take away parts of the end-to-end data. And we can see in the blue curve, that's the attention passing model. Even when we have only 25% of the end-to-end data in the training, we are still doing almost as good as the cascade. So of course, in the future, we would like to move this curve even further to the top right corner, but this is already quite a big improvement over the previous model. So for a somewhat more realistic experiment, this time we will keep all of the in-domain data and add a large out-of-domain machine translation corpus on top. So no additional speech data, just additional machine translation data. So these are the same numbers I showed before, showing that we get good overall accuracy with the attention passing model. And now this is what happens when we add the OpenSubtitles data, machine translation data into the training. And well, all of the models improve, which is good. But if you take a closer look, the direct model actually improves a lot less strongly than all of the other models, which again verifies the claim that the direct model is not very data efficient, at least as compared to the other models. And in fact, we can see that that the two-stage model overtakes the direct model after adding this additional data. And the attention passing model is the one that achieves both good overall accuracy and good data efficiency. Okay, so before I finish, I would like to mention a couple of contemporaneous works that are related to this work. The first one is by Gia et al. Called Leveraging Weakly Supervised Data to Improve End-to-End Speech-to-Text Translation. And there the authors address a similar problem, namely this data problem or data efficiency problem. And whereas our approach is to adjust the model to become more data efficient, here the authors synthesize the missing data points in order to solve a similar problem. So that's another way. And then on Monday, Liz Zaleski presented her work on phoneme-level speech representations, which is somewhat a similar idea to this one, except that everything moves to the pre-processing stage, whereas here it was all done in a single model. Okay, so to conclude, we've proposed this new model, which we call an attention passing model for end-to-end speech translation, and compared it to prior work and demonstrated both better overall accuracy and better data efficiency. Yeah, thanks.